Hi everybody, welcome back to my SP2 channel. So this is going to be all about the Bohr model. There's going to be an introduction and then all the details of this model. We're going to be looking at the energy states of specifically hydrogen atoms. I have a little bit about the limitations of this model, and then we also have a practice with you at the end. Okay, so in the discussion of the light and the electromagnetic radiation, there are going to be a few vocabularies that we just need to know them. Okay, so starting by spectrum, which is going to be the range of different wavelengths of your electromagnetic radiation. It can be emitted, it can be absorbed, it can be transmitted, and it has to be by a specific substance, right? Now, you can have your spectrum as a kind of continuous one or maybe discrete, depending on the source, and we're going to be looking at them in just a moment. Okay. The other term, which is pretty common, is monochromatic radiation. And monochromatic means that we have, the specific electromagnetic waves of a single wavelength or frequency. Okay, they're going to be a single color, for example, if you have it in a visible spectrum, and it's often produced by laser, you probably heard about that, or like a specific atomic transitions. Then we have the polychromatic radiation, and these are the ones that are going to contain multiple wavelengths, right? So poly means multiple wavelength or even frequencies of the light. And if you look at like white light, right, from the sun, or maybe, just a lamp, right? These are just the simple examples of the sources that are producing polychromatic radiations, right? They're going to be containing all visible wavelength, okay? Okay, so for the other two common terms, and those are the continuous and line spectrum, that's what I have for you on this page. So starting by continuous spectrum, typically consists of a range of wavelength where we have no gaps between them. It can produce if you have, very hot object, let's say you're looking at the sun or you have a light bulb, they can emit these lights. If the light passes through a prism, it actually forms a really nice gradient of colors from red to violet. Then we have the line spectrum on the other hand, where they are consist of, very distinct separate lines of a specific wavelength, and typically you see them on a very dark background. And this happens when we have the atoms that are emitting or maybe absorbing light at particular energy level. The examples could be something like hydrogen emission spectrum and a spectra of many other elements that we typically use them in our spectroscopy experiments. Okay, cool. Okay, so let's take a look at Bohr model. So this model was proposed by Bohr in 1913 to explain the structure of the atom, specifically the behavior of the electrons in hydrogen atoms. Take a look at the right side. So this is what I have for the nucleus, where we have all the heavy particles, right, protons and neutrons, and then the electrons are going to spin around it, just like what we have for the solar system. The sun is going to be in the center, and all the planets are going to move around the sun, right? And they're going to have their movement at a very fixed distance from the nucleus. They call them the quantized orbit, right? Meaning that the electrons can only exist at a specific distances from the nucleus, okay? These electrons do not spiral into the nucleus, which is pretty much what is given by the classical physics, okay? Okay, so let's go a little bit deeper on the, postulates or the assumptions of this model. So the first one is the one that we briefly mentioned about, the quantized energy or the quantized orbits. And here it says that only specific orbits with, very certain radii or discrete energy levels are going to be allowed for the electrons in the hydrogen atom. Okay, so these orbits are going to be corresponding to the quantized energy states. Now, can we have the transition between the energy level? Yes. Okay, so if I have absorption, that means an electron is going to absorb energy, right? It could be from light or from heat, and it can jump to the higher energy level. This is what we call excited state. Okay, and then I also can have like emission, right? If the electron releases energy, right, when it falls back to the lower energy level. Okay, so they're going to be more about this, excitation, absorption, emission, relaxation, right, as we go over the, future lectures. Also, the last thing that I want to mention here is the equation that we have used previously, right? We can use that for the Bohr model as well, right? So we have this quantized energy, which is our photon, and that goes by the h, which is our Planck's constant, times by the frequency of the emitted or the absorbed radiation, okay? Okay, so let's go deeper in the energy states of hydrogen atoms. So this slide is going to be covered by a lot of equations, okay? Just get ready for that. So from this model, Bohr model, we are getting our energy based on this equation, right? So the energy of our electron at any level, right, we call that N, goes by negative, and then I have RH, which is our Rydberg constant given here in joules, and then you divide that by n squared, and n is known as the principal quantum number, okay? And that is going to be starting from 1, so it must be an integer number starting by 1, right? So 1 is going to be the first orbit next to the nucleus, and then n equal 2 would be the next one, right? As we go higher in the n value, we're going to have higher energy, right? Okay. Now, if you're looking at the movements of the electrons between the energy level, right, then we have to go by delta E, which is going to be always final minus initial. So pretty much you're writing this formula twice, right, and you take a difference of them, right? Okay, then I'm going to go ahead with my Planck's equation, and I'm going to, replace my energy by hc over lambda, and a little bit kind of rearrangement here. This is going to give us the, ultimate equation for calculating the wavelength of our transition, okay? And I have this R prime H, which is the Rydberg constant, but in terms of the wavelength, okay? So what can I get out of this equation? If I have my final state higher than my initial, then I'm expecting to have the photon being absorbed, which means that you're looking at the positive change in your energy. But if your final state is less than your initial one, we're going to have the photon emitting the light, right? That will be a negative change. So your delta E is going to be negative, right? So be careful with this positive, negative absorption and emission of the light, okay? Excellent. Okay, so take a look at some of the limitations or like restrictions for this Bohr model. Okay, so we kind of like it when it comes to just one electron system, right? If you have like hydrogen or hydrogen-like species, let's say helium plus or like lithium 2 plus, where we only have one single electron, this is going to be very helpful. You can definitely study the structure using the Bohr model. But if you have more than one electron, right? Let's say you have helium or like carbon or any other atoms other than hydrogen, they are going to have more than one electron. And this model is not going to be helpful in studying their structure because the model does not know anything about the electron-electron interactions, okay? The second thing is about the quantized energy levels, which is successfully explained by this model. But Bohr assumed that we have more like a circular orbit around the sun, like planets around the sun. But if you look at the actual observation of what we have from the lights and the energy, the expectation is we have some sort of, electron orbitals, right? And we'll talk about that in our quantum mechanic discussion, which is a very advanced model, right? Okay, there's another thing, and that's about the chemical bonding and periodicity. So it is definitely working for the individual atoms, right, of hydrogen, but it's not going to tell us anything about how the atoms are kind of binding to each other and forming molecules. There's nothing about the periodic trends, right, in our periodic table, or even the, electron shielding and effective nuclear charge. And these are going to be a lot more like advanced discussion, and we talk about them as we progress, right? They're going to be covering in our future lectures. But the more Bohr model, right, does not able to explain these observations. Okay, beautiful. Okay, so that brings us to our practice. So take a look at this long question stem. It says in the Bohr model of the hydrogen atom, electrons are confined to orbits with fixed radii, and we can calculate these radii. Okay, these are all given here by the question stem. The question is, what is the energy and the wavelength of the transition from 4 to 1? So if I have an electron on n equal 4 and it's kind of coming back to my n equal 1, they're going to have releasing of the energy, right? So that change must be a negative change, right? And I'm going to just, replace my RH, which is my Rydberg constant here. For my final is going to be 1, right? And your initial n is going to be 4. So just plug in the values and grab your calculator, right? And you can calculate this energy. Okay, so we've got the energy. The next step is calculating the frequency. So I've got my energy. I need to divide that by my h, which is my constant, right? Planck's constant. And that is going to give me my frequency. And then lastly, you can use your speed of light over your frequency to calculate your wavelength. Okay, cool. That is going to be it for this lecture. I hope you like it as much as I like it. Thank you so much for watching this video. Don't forget to give it a thumbs up if you like it, right? And if you want to continue learning with me, you just need to subscribe, and that's it. That's all I'm asking you, okay? Take care of yourself, and I'll see you soon for the next lecture. Bye-bye for now.